Hello everyone and welcome back. My name is Mr. Kowald, and in this video we're going to be going over the properties due to intermolecular forces. Now in my previous video I talked about the polarity of bonds and the polarity of molecules, and that had to deal with inner forces that were holding the atoms of a molecule together. Here we're going to be looking at what kinds of forces, or the forces that hold or that hold the molecules together, that occur between molecules. So let's get into this. So let's talk about some vocabulary that I was kind of getting into. So the first thing we want to talk about is intramolecular forces. Intra means within or inside. So here, when we're talking about intramolecular forces, we're talking about the forces within a molecule, the forces that are holding the atoms of a molecule together. So these are the forces holding together atoms inside a molecule or a compound. These are what we think of as bonds. So these are going to be relatively strong, and the types that we've talked about before would be ionic bonds and covalent bonds. So those are examples of intramolecular forces, because the ionic bonds and covalent bonds are what hold the atoms of a molecule or compound together. The other vocabulary word we want to learn is intermolecular forces. Now, intermolecular forces, inter means between. So these are going to be the attractive forces between the molecules, not within a molecule. And so when we're talking about intermolecular forces, we're talking about the attractions or the repulsions that act between neighboring molecules. So these attractive forces are going to be holding different molecules next to each other. They're relatively weak compared to that of the intramolecular forces, ionic bonds and covalent bonds. So ionic bonds and covalent bonds are relatively stronger than the intermolecular forces that occur between the molecules. And so these intermolecular forces are not strong enough to be called real bonds. So um, so in the bottom here of the slide, here we have our two hydrogen chlorides, or HCl molecules. The bond, the covalent bond that's holding the hydrogen and chlorine together, that's your covalent bond, and also the covalent bond holding these together. So the covalent bond here and here are your intramolecular force. These are relatively strong. Now, the attractive force between these two molecules is what we call the intermolecular force, which is relatively weak, and it's represented by this dotted line here. Now, why is there this attractive force? For in this case, we learned in my last video that this is a polar molecule. Why is it a polar molecule? Well, because you have two different atoms, chlorine and hydrogen, bonded together, and they're sharing electrons. Chlorine is a higher electronegative atom, so it's going to be pulling on those electrons in the bond more. This is like the polar bear and the penguin example. The hydrogen has a less electronegative atom, so it's like the penguin, and the polar bear is the chlorine, and they're holding on the ice cream cone that has two scoops of ice cream. So here, the electrons are being pulled more strongly by the chlorine, just like the polar bear would be pulling on the ice cream cone more strongly. So that would make this a polar molecule, because it only has one bond, and the bond is polar, so therefore the molecule is polar. That means that hydrogen has a partial positive charge on it, and the chlorine has a partial negative charge. And so if this hydrogen on this molecule is partially positive, and the chlorine on this molecule is partially negative, and we know that opposites attract, then the negative chlorine on this molecule will be attracted to the positive hydrogen on this one, and that's what creates the intermolecular force. So here is an example of water. Water, if you remember, is a polar molecule. Oxygen is more electronegative, hydrogen is less electronegative, and so hydrogen is going to be partial positive. So these hydrogens are partially positive, the oxygen is partially negative, and so you have a negative side of your water molecule and you have a positive side of your water molecule. So it's polar. And so the partial positive hydrogens of one molecule will be attracted to the partial negative side of another water molecule, of the oxygen on another water molecule. So again, you have the dotted line between the positive hydrogen here and the negative oxygen here. The positive hydrogen here, the negative oxygen here. So you got a intermolecular force here and here. You got one here. So all of the neighboring water molecules are attracting each other through these partial negative and partial positive charges between the neighboring molecules. And so that's what's creating the intermolecular force. So we use dotted lines to represent these forces. These forces are not real bonds. They are much weaker than the intramolecular forces, the covalent bonds holding the hydrogens and oxygen together. So this dotted line represents that this is not a complete bond. It's not as strong as the covalent bonds that hold the atoms together in your water molecule. So one thing to keep in mind, this is the key point for this video, is that if there are a lot of intermolecular forces, or IMFs for short, then the molecules will be held near each other like a bunch of magnets. So if you've got your intermolecular forces between the molecules, that's like having magnets bunched together when they're near each other. So as we know with magnets, the stronger the attractive force between the magnets, the more tightly they're held together, the stronger they're held together, and therefore the harder it is to separate the magnets. It's the exact same thing with the water molecules or with intermolecular forces. The stronger the intermolecular force, the stronger they're held together and the harder it is to separate the molecules. So this leads to some properties that substances have due to the intermolecular forces. So again, thinking of intermolecular forces, if the intermolecular forces are strong, then it's going to be harder to boil something. So boiling is when you change something from a liquid to a gas. Well, in order to go from a liquid to a gas, you need the molecules to separate from each other, right? That's what boiling is. Boiling is going from a liquid to a gas. In order to go from liquid, where the molecules are close together, to where they are far apart in a gas, means you got to separate them. You got to get them to overcome those attractive forces. Same with melting point. Melting is where you go from a solid to a liquid. So if you have ice, which is solid water, the water molecules are held into place, they're stuck in place, they're not moving because of the attractive forces. But if you put energy into the ice, if you heat it up, then you can put energy into the molecules, you can get them to move, and that will overcome the attractive forces and start to melt. But the stronger the attractive forces between the molecules, the more energy it's going to take to separate out those molecules. Viscosity is related to how easy a substance flows, right? So viscosity is a resistance to flow. So the more viscous something is, the less it flows. The less viscous something is, the more it flows. And then we have surface tension. Surface tension is a measure of the energy it takes to separate your molecules at the surface of a substance. So if the molecules at the surface of a substance are attracted strongly to each other, then it's going to be harder to break them apart. It's going to take more energy to overcome those attractive forces at the surface of your water. Um, so this is why when you dive into water, you break the surface and you're able to go in without much pain. But if you do a belly flop, um, the surface tension is holding you up. This is also why certain light bugs can float on water. They can walk on water because the surface tension is holding them up. Um, so, how do the intermolecular forces relate to these properties? Well, when you increase the IMFs, the stronger the IMFs, the more IMFs you have, the more intermolecular forces, the stronger the intermolecular forces, these properties are going to increase too. So that means that the more forces that are present in your substance, the higher these properties will be. And so that means that if you have stronger intermolecular forces in your substance, that means your boiling point is going to be higher. It's going to take more energy to cause the substance go from a liquid to a gas. If you have stronger intermolecular forces, that means your melting point is going to be higher because it's going to take more energy to separate your solid, the molecules in your solid, to get that to become liquid, to get those molecules to move. The same for viscosity, right? So the stronger the intermolecular forces, the stronger they're held together, the less likely they're going to move and flow. So higher intermolecular forces, stronger intermolecular forces means less likely to flow. It's more viscous, thicker. And finally, surface tension is going to be higher. Stronger intermolecular forces means that you have higher surface tension. It's going to be harder to break the surface tension. It takes more energy to do that. So all of this is because it is harder to separate the molecules. So again, the main point here is that stronger intermolecular forces means that the molecules are attracted more strongly to each other. So they're going to be more strongly stuck together, and it's going to take more energy to separate them. So not all substances are going to mix. So another relationship, another property is the ability to mix with each other, right? So not all substances will mix with each other, with other substances. So think of oil and water. They don't mix. Oil and water don't mix. Polar substances like to mix with other polar substances. So there's a likeness there. So if you have one polar substance, it's going to mix with another polar substance. If you have non-polar substances, they're going to like to mix. So a non-polar substance is going to mix with another non-polar substance. So they're like each other. Polar substances, however, will not mix with non-polar substances. And so this brings us to a rule that you might know called like dissolves like, or like mixes with like. Dissolving is the same as mixing. So like dissolves like. So if if I what that means is that substances that have the same polarities are going to mix with each other. So polar substances are going to dissolve or mix with polar substances. Non-polar substances are going to mix and dissolve other non-polar substances. And so this is related to the miscibility of a substance. Miscibility comes from the Latin word for mixing. So if this new property, so a property of miscibility, are these substances miscible? Well, that means are they going to mix together? Are they going to dissolve each other? And the answer to that is, do they have the same intermolecular forces? Are they polar? If they're both polar, they will mix together. If they're both nonpolar, they will mix together. If one is polar, the other is nonpolar, they're not going to mix together. So let's look at some examples. So we have HBr and Br2. So are these going to mix together? Well, HBr, is that polar or nonpolar? That's going to be polar because you have hydrogen and bromine bonded together. Those are different atoms. They're going to have different electronegativities, and therefore the bond is going to be polar, and therefore, since HBr only has one bond, then the molecule is polar. Br2 is two bromine atoms bonded together. It's the same atom bonded to each other, same atom bonded to each other, and so you have this equal electronegativity. There's no difference in the electronegativity, so this is going to be a nonpolar molecule. So we have a polar molecule and a nonpolar molecule. We know the rule is like dissolves like. These are not like each other. We have polar and nonpolar. So therefore, they're not going to be miscible. They're not going to mix together. So the other thing we can know is that HBr is going to have a higher boiling point because of the polarity of the molecule. Because remember, the polarity means that you have a positive and a negative, and that's going to be an attractive force holding the molecules together. Nonpolar molecules don't have those attractive forces, and so they're going to be weaker. The intermolecular forces are going to be weaker between the bromine molecules. So that means since HBr has stronger intermolecular forces, the HBr is going to have a higher boiling point, it's going to have a higher melting point, it's going to have higher viscosity and higher surface tension. Okay, what about HBr and Br2 with regard to mixing? Are they going to mix together? They're polar or nonpolar, and HBr is not going to mix with Br2 because, again, the rule is like dissolves like mixes with like, and since they're not alike in their polarity, they will not mix. Okay, what about fluorine and bromine? So bromine here is a nonpolar molecule because you have two bromines bonded together. They have the same electronegativity. They're sharing the electrons equally, and so therefore it's nonpolar. And the same can be said for fluorine because you have two fluorine atoms bonded together. Both fluorine atoms have the same electronegativity, so they're going to be sharing the electrons equally. So both are nonpolar. Okay, so what does that mean? Well, they're going to mix. Like dissolves like mixes with like. So because these are both nonpolar, they're going to mix. What about water and CO, carbon monoxide? Water has polarity because we saw that it's a bent molecule. It has lone pair electrons on the oxygen. Those lone pair electrons are going to push the hydrogens to the one side of the molecule. Remember that the bonds are polar between hydrogen and oxygen. Hydrogen has a partial positive charge, oxygen has a partial negative charge, and so therefore you have a positive side and negative side of your water molecule, so it's polar. And the same thing for carbon monoxide. Carbon is bonded to oxygen. Oxygen is more electronegative. Therefore, it's going to pull the electrons more, and it's going to create a negative side and partial negative on the oxygen and a partial positive, excuse me, on the carbon. And so that's polar 2. And so therefore, since they're both polar, they have the same polarity, they're going to mix. Like dissolves like mixes with like. Okay, so that's it for this video. There are other videos that I will post in a moment that you can watch. Thanks for joining me on this video. I hope you enjoyed it. If you enjoyed this video, if this was helpful in any way, then please like, share, subscribe to my channel, like the video, share the video. Make sure you hit that notification bell. When you hit the notification bell, make sure you click all so you can be notified of all videos I put out. And put a comment down in the comment section. Let me know what you think, and if you've got any questions, I would love to hear from you. Thanks for joining me, and have a great day.